Hey there, Dave here. Welcome to Logic. This video I want to tell you a little bit about what Logic is, a little bit about what we're going to be doing this semester, and go over some of the material that you're going to need to do your first homework assignment, which is due at the end of the week. All this material is in your lecture notes, the first lecture notes, which you already have access to. So Logic is kind of a weird beast. It's a thing that sits in between a bunch of different disciplines. So some logicians, like me, are philosophers. Other logicians are computer scientists. Others are mathematicians. Others are linguists. Others are electrical engineers. Logic is an interdisciplinary area of study that sits at the kind of intersection and boundary of all of these fields. Part of why it can do that, part of why it can sit at the intersection and boundary of all of these fields, is because of how abstract it is. The sorts of patterns and the sorts of systems that logicians study and work with are the kinds of patterns and systems that arise in all these different areas. Let me start by giving you an example of that. So here we are. Think about the following sequence of symbols. I'm going to write an N, an arrow, and an S, and an N. Draw a line under it, and put an S. You're going to see this kind of thing a lot this semester. And here's what this sort of thing means. This N arrow S is going to be one thing. We've got components N and S, and they're put together by an arrow. Then there's that N again over there. So here we have two different things above the line. N arrow S is one of those things, and N is the other. And then below the line we have this thing S. And you should understand this as saying, when you have this thing, and we'll talk about what the thing is in a second, when you have this thing and you have that thing, then you can pass to that thing, right? So once you have the requirements above the line, you get what's below the line. Now let's think about some different interpretations of this kind of thing. One thing, if you've studied philosophy in the past, you might have heard of a very common argument form called modus ponens, and this could represent an argument of that form. For example, this might mean something like, with the arrow here to mean if, the whole thing might mean something like, if the coronavirus is in North America already, then it's in South America already too. Now N claim the coronavirus is in North America already, so conclusion, it's in South America already too. That's an argument form called modus ponens, and you can see this form as representing that argument form. But it's not just arguments that can be represented by this form. So for example, suppose you were instead interpreting this as telling you about computer programs. This might tell you, again with the arrow representing that connection, that you have a computer program that can take a number as an input and produce a string of text as an output. Then this would tell you, oh, and I have some particular number. Well, what you could do then is run that program on the number and produce a string of text as the output. So in that interpretation, the N and the S are not claims, but rather types of data. The very same form that we use to look at the argument form of modus ponens in philosophy is a form that we can use to look at this kind of calculation. And finally, for a third interpretation, we can think about this in linguistics as telling us about how to put a sentence together. So you might take a word like runs, and you might see a word like runs as something that, when combined with a noun, gives you a sentence. That's what thing that arrow could mean, right? The N for noun, S for sentence. You might see runs as an N arrow S. That is something that, when combined with a noun, gives you a sentence. Then you could take a noun, like, for example, the name Mary, and form a sentence. The sentence, Mary runs. So again, this very same form tells you about how to put these things together to get this sort of output. So this one form, this is something that we'll look at this semester. We're going to call it implication elimination. You don't need to know that for now. That'll be part of what we talk about in week 3. But this one form captures simultaneously all of those different things. Captures the argument form of modus ponens, captures applying a computer program to a piece of data, and it captures putting together a sentence made of a verb and a noun. This is part of where logic gets its power from, because we're going to be studying forms like this directly and in their own right. We're going to learn things that then have lots of different applications and can get a lot of traction in a lot of different areas simultaneously. There are lots of different tools and techniques that people use when they're studying logic. Some of the most common tools are things called proofs and things called models. We're going to be looking this semester at very simple forms of both. We're going to spend a bit more time on proofs than we do on models. We're going to start with proofs and spend the bulk of the semester there. Then towards the end of the semester, we're going to shift to looking at some very, very simple kinds of models as well, to give you a sense of the range of technologies and tools that we tend to use in logic. So let's start by thinking about a proof. Proofs, as we look at them this semester, are always going to be two-sided. They're going to be proofs from something, and they're going to be proofs of something. So a proof is a proof of some conclusion, something it's trying to establish, something it's trying to give support to. But a proof might take all kinds of different things for granted. A proof might not start from absolutely nowhere, but might have various assumptions in play. And so we're going to think of a proof as a proof from those assumptions of its conclusion. One thing proofs do is allow us to investigate things we couldn't investigate otherwise. So think about numbers, for example. There are lots of different ways to write numbers down, lots of different number writing systems, right? You could have a Roman numeral 3, you could have the Arabic numeral 3, which we normally use. There are lots and lots of other writing systems that have different ways of writing down different numbers. But all those different ways of writing down, say, the number 3, are ways of writing down the same thing. That number 3 is not a particular way of writing it. It's something else. It's a number. Numbers are invisible. Nobody's ever seen them. Nobody's ever come across one. You might have seen 3 apples. You might have seen 3 pens. You might have seen various numerals written down to represent 3. But 3 itself isn't the kind of thing you can just bump into. It isn't the kind of thing that you can investigate with a microscope. It isn't the kind of thing that you can investigate with a telescope or chemicals, or the sort of usual techniques that we use to investigate the world around us don't really work on abstract things like numbers. What does work to learn about abstract things like numbers is proof. We can prove things about numbers, and that's one of the only ways we really come to know anything about them. So here's an example of a proof that might help you learn something about numbers. First, you need to know what a prime number is. A prime number is a number that can't be divided by anything other than itself or the number 1 evenly. So 2 is prime because it can only be divided by 1 or 2. 3 is prime because it can only be divided by 1 and 3. 4 is not prime because in addition to being divisible by 1 and 4, it's also divisible by 2, by something else. 5 is prime again, 6 is not because it's divisible by 2 and 3, and so on. So you might wonder, how many prime numbers are there? Well, you can't go out and look and count them up because you can't see the numbers. Here's what you can do, though. You can find out with a proof. There are infinitely many prime numbers. They keep on going forever. But here's how you can see that. Suppose, instead, that there weren't. Suppose there was a limited number of prime numbers. Suppose we could have a finite collection that contained all the prime numbers that there were. Well, then one thing we could do is multiply all those numbers together and add 1 to the result of multiplying them all together. We'd get some really big number. I don't know how big, but whatever. All the prime numbers multiplied together plus 1. Now think about that last number that we've arrived at. One thing we know is that it can't be one of the prime numbers because it's bigger than all of them, right? We multiplied them all together and then added 1 to the end. This thing's way too big to have been one of the numbers that we started with. So it's not a prime number. But another thing that we know is that every number that's not a prime number is divisible by some prime number. This thing, though, isn't divisible by any of the prime numbers because of that little 1 we added at the end, right? It would have been divisible by all of them, but then we add 1, and so it throws everything off, and it's not divisible by any of them. So we've reached a contradiction. This thing can't be prime because it's too big, but if it can't be prime, then it must be divisible by some prime number, and it's not divisible by some prime number. So something's gone wrong. What's gone wrong? Well, our initial assumption that we had this finite collection of prime numbers, that was the problem. There is no such finite collection of prime numbers. So to think about that reasoning now in a more schematic form, right? We suppose we have a finite collection of prime numbers. From that, we get this other number, and then we derive a contradiction from the existence of that other number. We say, okay, that other number has to be prime, but it can't be prime. So we conclude that our initial assumption was wrong. Our initial assumption was that there are only finitely many prime numbers. That was wrong. We conclude there must be infinitely many prime numbers. So that's a proof. We've learned something about prime numbers. Proofs are the tools that we have for exploring these abstract domains. This is one reason reasoning like this can be so useful in philosophy, where a lot of what we reason and think about is very abstract. It's also another reason that these are usable in areas like computer science, because while computers are concrete objects, the information that flies around inside them, the information that they process, can be treated in this kind of abstract way. So let's get started on some of the material that we're going to take a look at this semester, and this is going to be material that's in your initial lecture notes for lecture 1. When we're thinking about proofs, and we're going to be thinking about proofs a lot over the next several weeks, proofs, as you've seen, are bits of language, something that takes place in some language or other. Now, this can be a language that people actually speak, a language like English, which is the language we'll be using in here, or it can be in artificial languages of various sorts, various kinds of computer languages have important connections to proof. What we're going to do mostly in this semester, the proofs that we look at, are not going to be in a language that anyone actually uses. They're not going to be in a language that people speak. They're not going to be in a computer language. They're going to be in a very simple language. And this very simple language is designed by logicians precisely for its simplicity. This language is designed so that we can understand just the bare bones of what it is to be a proof and of how these proofs operate. If you go on in logic, if you're interested in studying applications to languages like English or computer languages or any other kind of language that is available to you, that's all out there, that's way more complicated than anything we're going to do this semester. We're going to start from the basics, just get a basic idea, and so we're going to use a very simple language just to get some practice with the ideas of proofs and models. So the first thing we need to do is think about what this language is, how this language operates. So here's how our language is going to work. At the basis, we're going to have some things that we're going to call atomic sentences. And those we're going to write P, Q, R, etc. I'm just going to use individual lowercase letters to represent those. And if you want to think about those as sentences, you should think of them as making entire claims. So maybe P is the claim that the moon is made of green cheese, and Q is the claim that there's a dog a few floors below me barking, and R is the claim that it's a beautiful sunny day outside, and so on, right? You can think of these as simple sorts of claims. In addition to having all of these claims, we're going to use things we call connectives to combine these things into larger sentences. And we're going to meet a number of connectives in the course of this semester, but the ones I want to look at today are just two. One's going to be written like that, and one that we've already met is going to be written like that. And I'll call this one conjunction, and I'll call this one implication. And these connectives work like this. Whenever we have sentences, we can put two of them together using a connective to form a more complex sentence. So, that's a sentence. We'd pronounce that P and Q, or the conjunction of P and Q, because what we've got are two sentences, P and Q, and they're on either side of that connective, putting them together. Similarly, that's a sentence. P implies R, or the implication from P to R. What we have here is two sentences, P and R, connected, again, with that connective, with that implication connective. We can also continue this process and build more and more complex sentences. So, for example, this whole thing is now a sentence, right? It's a conjunction. It's the conjunction of P with Q and the implication from P to R, or you might pronounce it P and Q and P implies R, or you might call it the conjunction of P and Q with P implies R. There are a lot of different ways to pronounce this sort of stuff. That's not really important. What's important is that you see how to write it down and how it all comes together, right? So we've taken these two sentences now, the sentence P and Q and the sentence P implies R, and we've used a conjunction to combine those sentences together. And this whole process can continue, right? You might take that whole sentence and now say it implies T, and now we have an even bigger sentence, right, where it's the conjunction implies this other thing, and what's it a conjunction of? Well, itself a conjunction and implication, and so on and so on and so on. So these sentences can get quite large and complex. One thing you've probably noticed as I was putting that sentence together, I'm using things like parentheses and bracketing and so on to indicate how the sentence is structured. It's important to be able to look at a sentence and unambiguously tell how that sentence is structured. So that means that something like the following is not a sentence at all. Right? So this looks like we're trying to use conjunction to put these sorts of things together. But remember, conjunction has to take two sentences and put them together into being one. What we have here are three sentences and two conjunctions, and there's just not really any way to understand what it is. So that gets a frowny face with fangs. No, don't do that. That's not a decent way to go. If you find yourself writing something like this, there's probably one of two things that you mean. Of course, I don't know which one it is. One thing that you might mean would be this, and the other thing that you might mean would be that. So you see, these are different sentences. This one is a conjunction. Its left conjunct is itself a conjunction, P with Q, and its right conjunct is just R. This one is also a conjunction, but it has a different left conjunct, just P, and a different right conjunct, this time the conjunction of Q with R. So these are both good, but they're different from each other. Just move the paper a bit so you can see that. These are different sentences from each other, and it's that parentheses that are used to indicate that. So the parentheses are used to indicate that grouping, to indicate that bracketing. When you're looking at sentences like this, it can be handy to have vocabulary to talk about the different parts of a sentence. So suppose we're looking at the sentence, say Q and S. This whole sentence is called a conjunction because its main connective is a conjunction. And that means that it has two components called its left conjunct and its right conjunct. And here the left conjunct is Q and the right conjunct is S. Similarly, if we look at a sentence like T implies R, because the main connective is implication, the whole sentence is called an implication, and this has its antecedent T and its consequent R. So that's just a little bit of vocabulary that helps us talk about the components that come together into compound sentences. Conjunctions have a left conjunct and a right conjunct, and implications have an antecedent and a consequent. In addition to that vocabulary, you're going to need to know how to identify the main connective of a sentence. And the main connective of a sentence is just whatever one came in last in putting the sentence together. So if you look at a sentence like T implies R, it only has one connective, so no surprise, its main connective is that implication. If you look at a more complex sentence like T implies R and S, like this, now the main connective is a conjunction, because that's the one that came in last. The implication, still a connective, but not the main connective. Now if you were thinking about a sentence like P implies Q and T implies R and S, like this, now the main connective is this conjunction, because this is the one that came in the last. All these other connectives, still perfectly good connectives, but they're not the main connective. When we interact with sentences throughout this semester, it's almost always going to be by way of thinking about their main connective. So what you want to do is get to a place where when you look at a sentence like this, you see that conjunction leap out at you as really the heart of the sentence. And when you look at a sentence like this, you see that conjunction leap out as the heart of the sentence. So let's think back to our two examples up here before, and think for a second, for each of these sentences, which connective do you think is the main connective for each of those sentences? You should be thinking, for this first sentence, that this conjunction is the main connective, and for the second sentence, that this conjunction is the main connective, right? So in both cases, the main connective is conjunction, but it's different occurrences of conjunction that count as the main connective for these sentences because they come in last. As long as you form your sentences properly, as long as you don't do any of this kind of horrible stuff, as long as you're putting things together in the right order and with good parenthesization, with good bracketing, in order to be able to indicate how it all goes, then it'll be very easy to tell what the main connective of your sentence is. It should be the connective that's outside of all the parentheses. And now finally, with that in hand, the last thing I want to go over today is the very first rule of our proof system. So we're going to spend the next several weeks building up a proof system that's going to allow us to make lots of different proofs in this language, proofs that use this kind of language, which is a very simple language. We'll meet some more connectives as we go along the way. It's not just these two connectives. You'll get some more in. There's going to be a range of different proofs that we're going to look at, but they're all going to live within this one proof system. And the way the proof system works is this. We're going to get a library of rules available to us, but these rules are not rules about what we can't do. These rules are all rules about what we can do. The general principle is that you can only build proofs via the rules that you have available to you. And the vast bulk of the rules that we're going to look at and use are rules that are connected to particular connectives. Conjunction will come with rules telling you how you can use conjunction. Implication will come with rules telling you how you can use implication. And the other connectives that we look at are going to come with rules that tell you how you can use those other connectives. But there is one rule, and that's the only rule we're going to look at today, that doesn't depend on any connective. It's a rule that allows you to form a proof from absolutely nothing. It lets you form a proof out of thin air. And the rule is called the rule of assumption. And that rule works like this. It says if you take a sentence and you write it down, so let's consider, for example, the sentence T implies R and P implies S. There's a sentence, I've taken it, I've written down. That thing, having written down that sentence, counts as a proof of that very sentence from that very sentence. So let's think about this. Remember, a proof is always a proof of something, its conclusion, what it's establishing. But it's also a proof from something. It's a proof from what's being assumed or from what's being taken for granted. So the rule of assumption says, if you take something for granted, then you can establish it on that basis. Right? If you assume something, you have successfully assumed it. That's basically what the rule of assumption says. At the moment, it shouldn't sound like that's terribly exciting or controversial, right? It basically just says, well, assume what you want to assume, and then, great, as long as you're assuming that, you've assumed it. What the rule of assumption does, basically, is it allows us to get our proofs up and running, to get them going. We need to start out by assuming something so that we have some material to work with in the course of a proof. And the rule of assumption says you can assume anything you want. And on the basis of that assumption, you count as having established that thing. At the moment, having assumed it, we can't do anything else with it. All we have is the rule of assumption. So there, I've assumed it. This is now a very small proof. There's nothing else to do. What the rest of the rules we're going to look at are going to do are going to give us the ability to manipulate proofs we already have. They're going to give us the ability to form more proofs and to do interesting things with these assumptions. But for now, all you need to worry about is how to generate the assumptions themselves, and you do that just by writing it down. So this thing here is a proof of T implies R and P implies S, and it is a proof with a single open assumption. And that open assumption is T implies R and P implies S. Let's look at another example. I think you probably see how it's going to go. Let's look at an example like that. That's just the sentence P. And standing on its own like this, this is a proof. It's a proof of the sentence P, and it's a proof with the open assumption P. Again, nice and simple. Incidentally, if you wanted to look at an atomic sentence like this and ask what is its main connective, the right answer is it doesn't have one, because there aren't any connectives at all. Only sentences that have connectives have main connectives. But this is still a perfectly good proof. It's a perfectly good proof of P from P. So that's how our rule of assumption works. As you take a look through your lecture notes for this week, you'll see a number of exercises to be done. Like every week, those exercises are due at the end of the week. So please do hop on those. If you have any questions about any of this or how this works, please do ask those questions on the Perusall site, which will give you an ability to tag the part of the reading that's most relevant to your question. I look forward to meeting you all next week in person, and I hope you have a great one. See you soon. Bye-bye.